So hello, we're back, and as promised we will start talking about mass conservation equation, the equation of continuity right here. And before doing this, I want to define a quantity called mass flux, or for that matter the flux of any quantity. Okay, it's defined like here, as I've written here. It's the amount of mass per unit area per unit time flowing out of or into a surface. In order to appreciate this, envisage a surface like this, a surface like this. It might be open or closed, that for the time being it doesn't really matter. And so you have mass either flowing out or flowing in. Okay, the units of mass are gram if you adopt CGS units. I'm most of the time, astrophysicists work in CGS, so I'm used to CGS, but not necessarily. I mean, if you're more comfortable with kilograms, that's all right. Okay, so the unit of mass per se is grams, but what we're talking about is the mass flux. Okay, so this would be grams per centimeter square per second. So this would be the mass flux, and this makes sense only if you consider a surface, because the centimeter squared here, what's it about? It's the mass per unit area, per unit cross sectional area, say some sort of a cross sectional area here. Okay, that's flowing out or flowing in per second, of course. Okay, so this is the definition of mass flux, and we will come back to this kind of a definition over and over again. Turns out that one can define something called a momentum flux as well, the flux of any quantity for that matter, which is momentum, whatever the units of that is, essentially grams centimeter per second, because it's MV, momentum per unit area per unit time. This is momentum flux. Okay, so this concept of flux will keep coming back over and over again during our discussion. So I thought I would take a moment to explain or to introduce what this is, and we will do so once again also as the need arises. Right, so getting back, so we've defined mass flux now, and so the mass flux is simply rho u, where rho is the matter density and u is the flow velocity. If you look at the units of rho, rho is the units of rho are grams per centimeter cubed, and the units of u are centimeter per second, right? So you multiply these two together and you get rho u something like grams per centimeter squared per second, right? Just to make it a little clearer, mass flux is rho u. This is grams per centimeter cubed, and this is centimeter per second, and therefore multiplied together the units of this are grams per centimeter squared per second. Okay, so that's how it goes. Right, so that's a definition of mass flux. And why is that useful? Consider this statement. The mass contained in a volume, which is the integral of rho dV, where dV is an elemental volume, it can change only due to mass flux through the bounding surface, because mass cannot be created or destroyed within the volume. Yeah, in other words, before looking at this equation, let's go back and do a little sketch. You see, suppose you have some kind of a bounding surface like this, And the whole point is you cannot magically create or destroy mass inside here. Yeah? So if there's a change in the mass flux inside here, that can either increase or decrease, that can only be because of mass flux flowing out or flowing in. Mass flux. Okay, either flowing out or flowing in like this. That's the only way the matter density inside this volume can change, right? And so what's the total mass contained inside this volume? Total mass contained is simply rho, the mass density times dV integrated over this whole volume, right? So that's what this says here. That's what this says. And so the rate of change of mass flux of the total mass, right? The rate of the time rate of change of the total mass, and this is the total mass, this integral is the total mass, is essentially the negative of the mass flux, which is rho u, integrated over the surface area. Which surface area? Well, the bounding surface. Okay. The first thing to notice is that the dimensions match up. I urge you to check that out. You just have a per second here. So this is grams per second, and the dimensions of this are grams per centimeter squared per second, and the dimensions of this surface area is essentially centimeter squared. So you have this was rho u dot ds. Okay, where ds is just this any small little surface element whose area vector is pointing outwards. So this is by definition, and this is of course centimeter squared. So this integral has units of grams per second, and that's exactly what the units are here. This is in grams per second, right? So it's an extremely simple statement to make. Mass cannot be created or destroyed inside this volume. Therefore, the only way the mass density, the total mass inside this volume can change is because of mass flux, because something is carrying matter away or inside this volume through the surface which is bounding this volume. That's what this equation is telling you. That's what this entire equation is telling you. Okay. So this is the same thing that we wrote here. It's exactly the same thing, no difference. And now we do a little bit of vector calculus. We apply Gauss's law to the right hand side to get the following. In other words, we convert the surface integral into a volume integral. So in doing so, this becomes this. All we're saying is that that's all we're saying, and this is so we apply this here to get something like this. Why did we do that? That's because you have a volume integral on the left side and a surface integral on the right hand side, a little awkward. So you convert both of them into a volume integral, and so you have a dV, and it's obvious, right? It's much more convenient. So you just take it to the left hand side and you write it like this, and we're almost there. And since this is true since this statement here, this entire statement is true for any arbitrary volume, no matter how small. Okay, and this is very, very important. Since this is true for an arbitrary volume, I should probably have written arbitrarily small volume. Okay, you can take this dV to be arbitrarily small, in which case the integral is irrelevant, right? So we can say that the integrand itself is equal to 0. Notice this is nothing but the integrand here. Okay, and that is it. This is the statement of mass conservation. This is the equation of continuity, and you might be familiar with this from electrodynamics as well. It's exactly the same. While doing electrodynamics, this would be rho would represent charge density. Here we're talking mass density. So that's all. This is the equation of continuity. What is it really saying? It's saying that mass cannot be created or destroyed. The mass contained in the volume can change only due to mass flux through the bounding surface. Mass flux through this bounding surface, right? So yeah, this one, I'm sorry, I meant this figure. So the only way the mass density or the total amount of mass inside here can change is because of mass flux through this bounding surface, and that is what at the end of the day, yeah, so that's what this equation is telling us, and this is called the equation of continuity. So there you have it. We've derived from intuitive considerations the continuity equation, and this is what's called the conservative form of the continuity equation. Okay, what you mean by that? I mean, this is just a word as such, but I will. So remember this word, conservative form. And really what this means, in general, the conservative form of any quantity goes as, in this case, it's a conservative form of the mass continuity equation. In general, the conservative form of any quantity goes as the partial time derivative of the quantity, in this case mass density, plus the divergence of the flux of that quantity is equal to 0. So the divergence of the mass flux. Remember, we said we spent a little bit of time in showing how rho u, this quantity, is the mass flux, right? So this is what's called the conservative form of the mass conservation equation, and so it takes the following form: the partial time derivative of mass density plus the divergence of the flux of mass is equal to 0. Okay, we will have an occasion to return to this particular conservative form for the momentum continuity equation as well. It's a little more complicated, but the concept is the same, right? So so there you have it. That's the equation of continuity. That's the equation of mass conservation, and we are done with the first of the conservation equations that we promised we would look into. So let's go ahead. Yeah, okay. So before that, recall in our study of kinematics, we had two kinds of derivatives. We had two kinds of, we had the Eulerian description, which is the description of the fluid flow as seen by a lab frame observer, an observer who is standing outside of the fluid flow. And we had the Lagrangian description, which is in some sense the fluid parcel frame, so to speak. In other words, it's the flow of the fluid as seen by an observer sitting on top of a fluid parcel. And the time derivative, while in this kind of description, was mostly, exclusively in fact, denoted by d over dt, whereas in the Lagrangian description the time derivative was denoted with these regular straight d's, right? You might wonder why I'm writing a partial here and why I'm writing a total here. I mean, the real reason is that, I mean, in the Eulerian description, things can change due to changes in time as well as changes in position. So the flow field is a function both of time and position, hence the partial derivative. Here in the Lagrangian description, you're sitting on top of the fluid parcel. There's only one variable, so to speak. Okay, so think about that, and we also made the connection between the two kinds of derivatives, the connection between this and we had like that. You recall we made this connection. Right? So this is how the time derivative in the Lagrangian frame and the time derivative in the Eulerian frame are related, and that's exactly what so this entire thing is written in the Eulerian frame. In other words, the lab frame in which the observer is standing outside of the fluid flow and he or she is watching the fluid flow by, and you can relate it using relation to the Lagrangian way of looking at things. This and this are both the mass continuity equation, except here the derivative is a Lagrangian kind of derivative. Okay, so this and this are exactly the same, and I would urge you to show this, to explicitly show how this follows from that or vice versa. Okay, this is a useful exercise. Sometimes it's more convenient to adopt the Lagrangian point of view. Sometimes it's more convenient to adopt the Eulerian point of view. It's important to be familiar with both kinds, right? So if you divide this entire equation by rho, on the right hand side you have 0, so that it makes no difference. If you divide this entire equation by rho, you get this. It's the same equation that we had written earlier, the mass continuity equation, right? In the Lagrangian frame as seen by an observer who is sitting on top of a fluid parcel. And one frequently encounters a situation where, to a fair approximation, the first term is negligible. In other words, this is often negligible. Okay. In which case, in other words, this is what I mean. This is the 1 over rho dt is approximately equal to 0. In which case, and you can see this. So suppose this was non-zero, right? Suppose this 1 over was equal to some constant k, right? So the solution to this equation would be some sort of rho equals rho naught e raised to kt, right? So in other words, the density is changing as a function of time, right? Suppose that's not so. Suppose the density is not changing as a function of time, right? In other words, the fluid is not squishy. You cannot change its density. The fluid is kind of it's what's called incompressible. This is the condition for incompressibility. That's what this equation is telling you. Okay. If that is so, if the first term is if this term is 0, then automatically follows that the mass continuity tells you that the divergence of u is 0. Many times this is simply taken to be the condition. This is simply taken to be the condition for incompressibility. Okay, so this divergence of u is 0. If the flow field is such that its divergence is 0, you immediately conclude that the flow is incompressible for this reason that we just discussed. And this is often, now it turns out that these are not absolute statements. It's never the case that a fluid is definitely compressible or definitely incompressible. It all depends upon how fast the fluid is flowing. And in physics, you never make this statement in an absolute sense. You never say how fast. Well, how fast with respect to what? With respect to the speed of light, or with respect to some other speed. Here we are talking non-relativistic dynamics, so the speed of light doesn't enter the picture at all. Everything, all flow speeds are much smaller than the speed of light. Turns out that if the flow speed is much lesser than the sound speed, which we have not introduced yet, we will introduce this when we start talking about compressibility. Okay, if the flow speeds are much smaller than the sound speed, then the any fluid can be regarded to be incompressible to a very good degree of approximation. Okay. Now I'll simply make this statement for now, and we will justify it later on when we start discussing compressibility. But this is something to be kept in mind, right? So what we've done for the time being is we have in a rather intuitive manner derived the equation of continuity or that of mass conservation. We have essentially derived two different guises of it, the Eulerian form of the continuity equation and the Lagrangian form of the continuity equation, and we've used the Lagrangian form of the continuity equation to derive what's called the incompressibility condition. Okay. Now this is a small variant to this. This is a small variant to compressibility or incompressibility, and it's a little bit of an advanced topic, but I figured I would mention this. This is not totally central to the basic flow of what we're talking about, but let's do it anyway. Yeah. So there's something called a Bossiness approximation, which is very closely related to incompressibility. You recall when we talked about compressibility or incompressibility, we were really talking about this. This is really what incompressibility was all about. In other words, the flow not being squishy. This is really what it was about. But turns out that you can, in other words, when you can neglect density variations, you say that the flow is incompressible. There's a related approximation called the Bossiness approximation, where density variations in the fluid can be neglected everywhere except where, by everywhere I mean in all terms of the equation, except where the density is multiplied by the acceleration due to gravity. Okay, so this is a little bit of a weaker condition than strict incompressibility. Okay. So density variations can be in all terms of the equation, whichever equation you're considering, can be neglected. So it's pretty much incompressible, except where the density is multiplied by g, you do not neglect density variations. Okay. For instance, consider a gravitationally vertically stratified atmosphere, which it's vertically stratified due to gravitation. An example, for instance, would be a container of fluid where the fluid is a mixture of various densities. Okay, oil, water, various other things. Okay, so what will naturally happen, simply because of gravity, there will be a stratification, and you'll have the densest material at the bottom. This would be the densest material. Yeah, and the next layer would be relatively less dense, and the next layer would be even less dense, like that. So this would be an example of so the density would increase like this. So this would be an example of a gravitational right. So So if that is so, then it turns out that, and this I will simply state without proof for the time being. As and when we start discussing isothermal flows, I would like you to show this fact, which is that the scale height of such an atmosphere, in other words, the scale height is essentially the height over which the density varies by a factor of E. Okay, so suppose the density is varying as e raised to some k z, then the scale height would be something like 1 over k. Okay, that's what the scale height is. So and we call that L, and that is equal to Cs squared over g, where Cs is the sound speed. I simply state this right now, but I want you to keep this in mind and derive this when we come to discussing isothermal flow. Now the thing is, this Bossiness approximation, which is a slightly weaker form of incompressibility, because density variations can be neglected in all terms of the equation except that term where the density is multiplied by g. Okay. Turns out that if this approximation is to be valid, the scale of the flow has to be much less than a density stratification height. In other words, say if the density stratification height was something like, about this, say about L, yeah, and this L is essentially this quantity. Okay. So if that was the case, then you want the scale of the flow, whatever flow is taking place should be much less than L. This flow should be confined to a vertical dimension that's much smaller than L. So under such circumstances, the Bossiness approximation is valid. Okay. Turns out, after having said all this, you'll be a little disappointed when I make this statement. The Bossiness approximation often just reduces to divergence of u equals 0, which was just what we said earlier. It was just what we said here. This is the incompressibility condition anyway, right? So the Bossiness approximation often just reduces to a divergence of u equals 0, but not always. Okay. So that is about mass conservation, and let us now march right ahead into momentum conservation.